Making the transition from learning data science to landing a role in the industry really comes down to two main pillars. First, you need to understand the formal interview pipeline, and second, you need to be comfortable mastering the architecture of modern AI systems, which includes concepts like MLOps. Let's break down the interview process first. It generally follows a structured multi-stage path. It all begins over here with the call reception, where candidates receive an initial screening call just to verify basic fit. Once you pass that hurdle, the process moves to recruiter handoff, where your CV is forwarded to specific hiring managers to see if your profile matches the team's needs. If there is a match, you enter the formal three-round progression. Stage 1 is the screening call. This is a brief conversation to check your communication skills and basic background. Next up is the technical interview. Here, you will face scenario-based questions and a coding round. Most companies require this as a mandatory filter, but don't panic. It usually focuses on basic logic and problem solving rather than high-level competitive programming. Finally, you have the client round, which is especially common in service-based companies. This focuses on how you would handle production and deployment for an actual client. So in summary, the whole journey moves from general screening to specific technical testing, ending with a focus on real-world deployment. Now, during those technical rounds, the questions often move beyond simple textbook definitions. You might be asked how to scale a deployment to thousands of users. This is where the right side of our board comes in. It's the practice of taking a model and making it work reliably in a real-world environment. When you combine those two, you get MLOps. To pull this off, you need a few key skills. First is Docker, a tool for containerization that packages your code so it runs exactly the same way on any computer. Second is Kubernetes, a system for orchestration that manages those containers, ensuring they stay running and scale up automatically if traffic spikes. And third, you need CI/CD pipelines. This stands for continuous integration and continuous deployment, an automated system that tests and deploys your code every time you make a change. Many candidates struggle here because they focus solely on the AI model itself. However, employers look for full-stack experience, including front-end and back-end skills, to ensure everything ties together. Ultimately, success in technical rounds requires knowing not just how to build a model, but how to deploy and maintain it as a reliable production system. Now that we understand the deployment architecture, let's look at what happens when those deployed models give unsatisfactory outputs and how we fix them using techniques like RAG and fine-tuning.
In the world of generative AI, a common challenge we face is when a model's output is simply unsatisfactory. For example, it might not know specific company data or it uses the wrong tone. To fix this, we rely on two main improvement strategies. The first is RAG, which stands for Retrieval-Augmented Generation. Think of this as giving the model access to a private library so it can look up the right information before giving you a better contextual answer. If RAG isn't enough to solve the problem, we move to the second strategy, which is fine-tuning to actually change the model's internal brain. There's a broader category for this called PEFT or Parameter Efficient Fine-Tuning, which focuses on changing as few parameters as possible to save time and money. Under PEFT, we have two primary methods. First is LoRa or low rank adaptation. This is lightweight because it just adds a small set of weights rather than changing the whole model. However, it's typically best if you have access to high-end GPUs. If you're working with limited resources, you'll want to use QLoRa. This is a more efficient version that compresses the data through 32-bit to 4-bit quantization, allowing you to fine-tune even on smaller hardware setups. So to summarize the technical side, we use RAG to give the model better context and fine-tuning to actually change its behavior. Now, understanding where you apply these skills is just as important as what you know. Let's look at the career guidance side. There are two main types of companies you might target. First are product-based companies like Google or Netflix. You will generally work on one long-term product. The work is predictable. You usually get a higher and more stable salary, And there is typically just one main interview loop. On the flip side, we have service-based companies like Accenture or TCS. Here, you work on various projects for different clients. This gives you a varied workload, but you might face bench periods with no active project, and you often have to re-interview every time a new client comes along. If you are a non-technical candidate or have resume gaps, don't worry. Your goal is to showcase your transferable experience. If you were in sales, highlight how you used analytics to make decisions. Always focus on your strengths. Finally, to land these roles, you need a repeatable interview preparation workflow. Start by taking the time to identify your question categories, like technical or competency questions. Then, draft concise answers that take about 30 seconds to say. After that, run mock interviews where you record yourself to adjust your tone. The absolute best way to structure these answers is the STAR method. This simply stands for outlining the situation to set the scene, the task that needed to be done, the exact action that you took, and the positive result that you achieved. By using the STAR method to structure your stories and rehearsing them, you'll present yourself as a highly capable professional. Once you've mastered these foundational improvement strategies and interview skills, you'll be perfectly positioned to understand how we orchestrate complex applications, like building an agentic RAG system that acts as an intelligent router for users.
An agentic RAG system is a major step up from a basic chatbot. Think of it as a highly intelligent dispatcher for a healthcare support system. When a user request comes in, it doesn't just blindly search a database. Instead, it hits this central agent, which acts as an intelligent router deciding the best path forward. This agent uses several specific tools. First, it passes the request through a query categorizer. This step analyzes the text to figure out what the user actually wants, whether they are asking about billing, setting up appointments, or checking their insurance details. At the same time, it checks the emotional tone using a sentiment analysis step. It evaluates those visual cues. Is the user happy, neutral, or highly frustrated? All this context feeds directly into the router engine, which serves as the core decision maker. Here is where the real logic happens. If the logic detects that the user is in distress, it completely bypasses the AI and routes them straight to an on-call doctor, getting them to a human professional immediately. However, if it's a standard query, the router sends the request down to the knowledge base. This is our vector database. The system performs a similarity search to find relevant documents, hands those facts over to the RAG generator, the AI's brain, which then formulates a helpful AI-generated answer to send back to the user. So, an agentic RAG classifies the query, checks emotion, and routes to either an AI or a human. But how does that knowledge base get built in the first place? Let's shift our focus to the right side, the knowledge base construction. To build the library the AI uses, we follow a straightforward four-step pipeline. The very first step is the document loader. This is where we ingest all our raw materials, like pulling in PDF files or connecting to API data streams. Next, because AI models have limits on how much text they can read at once, we use chunking. We split these massive documents down into smaller fragments, usually capping them around 500 tokens. Then comes the most crucial part, embedding. We use a model to translate those raw text fragments into mathematical vectors. Essentially, we are turning words into a list of numbers that represent their underlying meaning. Finally, we store these resulting vectors safely inside our vector database. Once this pipeline is complete, we have a searchable library that links directly back to our RAG system. So remember, building a knowledge base involves breaking files into small chunks, turning them into number vectors, and storing them so our intelligent agent can easily run similarity searches. Next, we'll dive into the specific tools needed to build this prototype in a Jupyter notebook.
Let's look at the building blocks for this prototype. We're working in a Jupyter notebook, which makes things easy. We use LangChain as the glue to connect our language models, or LLMs, with our database. For storage, we use ChromaDB, a straightforward local vector database. And to make it interactive without building a full website, we use IPy widgets for a simple text box. Next, we handle data preprocessing and vector store logic. In our healthcare example, we start with a JSON file. We separate the metadata, like the billing category, from the actual content of the questions and answers. When setting up our search, we tune 3 things. First, we set K to 3, meaning we pull the top 3 most relevant results. Second, we use a score threshold of 0.30, so we ignore any results that are less than 30% relevant to filter out noise. Finally, we use cosine similarity, a mathematical metric to measure how close the vectors are. Now for the smart part, sentiment-driven routing. When a message comes in, an LLM like GPT-4o analyzes its sentiment. If the user is in distress, they are routed to an on-call doctor immediately. If the sentiment is negative, the system connects them to human support to handle complaints. But if it's neutral or positive, the system gives an automated RAG response. This way, AI handles the routine, and humans handle the high-stakes situations. In healthcare, HIPAA compliance is absolutely mandatory. We must assure users that records are stored securely and access is limited to authorized providers. To enforce this, our system prompt is built to include a compliance disclaimer in every AI response. Finally, we look at evaluation metrics and debugging. We check 4 key areas: recall, asking if we found all the relevant info; precision, asking if what we found was useful; contextual relevancy, seeing if the answer matches the search; and hallucination detection, making sure the AI didn't make anything up. If you hit a status code 400 while debugging, it's often just a syntax error or duplicate node name. And that brings us to the payoff. You now have a comprehensive view of how to build, explain, and deploy a professional-grade